On December 14th, 1900, Max Planck stood before a room of physicists and shattered reality. Energy, he revealed, comes in indivisible packets, quanta. This radical idea cracked open a universe where particles could exist in superpositions, described not just as 0 or 1, but both at once. Today, quantum computers harness these rules, letting 300 qubits encode more states than there are atoms in the observable universe. But how does this mind-bending machinery actually work? And what secrets lie behind its veil? To unravel the mechanics and the stakes, we need to return to the origins, where the rules of our digital future were first written. At the dawn of the 20th century, the laws of physics seemed complete. Newton's equations described the motion of planets, Maxwell's theory unified electricity and magnetism, and energy was thought to flow in smooth, continuous waves. Yet, as scientists studied the glow of heated objects, these comfortable certainties began to unravel. In 1900, Max Planck confronted a puzzle that defied explanation: the spectrum of light emitted by a black body. Classical physics predicted an infinite amount of energy at short wavelengths, a result so unphysical it became known as the ultraviolet catastrophe. To resolve it, Planck proposed something radically new. Energy, he argued, could not be divided endlessly. Instead, it came in discrete packets, each one a multiple of a fundamental constant, now called Planck's constant. The formula he introduced, E equals h nu, changed the course of science. Planck's idea was not just a mathematical trick. It forced a rethinking of the very nature of reality, hinting that the world at its smallest scales played by rules far stranger than anyone had imagined. A generation later, Niels Bohr tackled another mystery: the structure of the atom. In 1913, he showed that electrons do not orbit the nucleus in arbitrary paths. Instead, they are confined to specific energy levels or shells, each one quantized. When an electron jumps between these levels, it emits or absorbs a photon of precise energy, a direct consequence of Planck's quanta. Bohr's model explained why atoms emit light at sharply defined colors, not the smeared-out rainbow predicted by earlier theories. The atom, once thought to be a miniature solar system, now revealed an interior governed by leaps and discontinuities. But the surprises did not end there. In 1927, Werner Heisenberg introduced a principle that would unsettle even the most seasoned physicists. He showed that it is impossible to know both the exact position and momentum of a particle at the same time. The more precisely one is measured, the less certain the other becomes. This relationship, delta x times delta p, is greater than or equal to h bar over 2, where h bar is Planck's constant divided by 2 pi, was not just a limitation of instruments, but a fundamental property of nature. The world at the quantum level, Heisenberg revealed, is built on uncertainty. Planck's quanta, Bohr's orbits, and Heisenberg's uncertainty principle shattered the classical view of a predictable clockwork universe. In their place, they left a landscape shaped by probability, discreteness, and limits on what can be known. These discoveries did more than rewrite the textbooks. They opened the door to the mathematics of superposition, where particles can exist in multiple states at once. The stage was set for a new kind of logic, one that would one day power machines capable of solving problems beyond the reach of any classical computer. A single qubit is not confined to just two possibilities. Instead, its state is described by alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers whose squared magnitudes add up to 1. This formula captures the essence of superposition. The qubit is both 0 and 1 at once, with alpha and beta setting the likelihood of each outcome. Unlike a classical bit, which must be either on or off, a qubit explores a spectrum of possibilities, living in a space defined by probability amplitudes rather than certainties. The power of this idea grows rapidly with each additional qubit. For n qubits, the system can exist in a superposition of 2, to the power of n possible states. With just 300 qubits, the number of simultaneous configurations exceeds 10 to the 90th. That is far more than the estimated number of atoms in the observable universe, which is about 10 to the 80th. This exponential scaling is what gives quantum computers their extraordinary potential. They are not just faster versions of classical machines. They process information in a fundamentally different way, holding and manipulating vast amounts of data in a single operation. This counterintuitive behavior is not just a mathematical curiosity. The double-slit experiment, first performed with light by Thomas Young in 1801 and later repeated with electrons by Davison and Germer in 1927, provides vivid proof. When particles like electrons are sent through two slits, they create an interference pattern on a screen, which is evidence that each particle behaves like a wave, passing through both slits at once. Block one slit, and the pattern vanishes. Allow both slits, and the pattern reappears, even if particles are fired one at a time. This phenomenon can only be explained if each particle exists in a superposition of paths, interfering with itself. Yet quantum possibilities do not persist indefinitely. When a measurement is made, such as detecting which slit an electron passes through, the superposition collapses. The outcome is either 0 or 1, left or right, with the probability of each determined by the squared magnitude of its amplitude. Max Born formulated this rule in 1926. The Born rule says the probability of 0 is the squared magnitude of alpha, and the probability of 1 is the squared magnitude of beta. The act of observation transforms the qubit's delicate balance of probabilities into a single, definite result. Until that moment, the qubit state is a cloud of potential, shaped by the strange mathematics of quantum mechanics. The interplay between superposition and measurement is at the heart of quantum computing. It allows a quantum processor to explore countless possibilities at once, but it also imposes a strict limit. Information can only be extracted through measurement, and measurement inevitably reduces the system to a single outcome. Harnessing this tension is the key to unlocking quantum advantage. In 1935, three physicists, Einstein, Podolsky, and Rosen, challenged the completeness of quantum mechanics with a thought experiment that would haunt physics for decades. They described a pair of particles prepared so that measuring one would instantly reveal information about the other, no matter how far apart they were. Einstein called it spooky action at a distance, and he believed it proved quantum theory was missing something, perhaps hidden variables that restored the certainty of classical physics. For nearly 30 years, this paradox remained an open wound in the foundations of science. Then, in 1964, John Bell, a physicist at CERN, devised a way to test whether the predictions of quantum mechanics could be explained by any local hidden variable theory. Bell's theorem showed that if quantum mechanics was right, certain statistical correlations between entangled particles would violate a mathematical inequality, something no classical explanation could match. The stage was set for experiment to decide what theory described reality. It was not until 1982 that technology caught up with theory. In a series of landmark experiments in Paris, Alain Aspect and his team created pairs of entangled photons and measured their polarizations at different angles. The results were unmistakable. The correlations between the particles exceeded the limit set by Bell's inequality, matching the predictions of quantum mechanics. Each measurement on one photon seemed to instantly affect the other, even when the detectors were separated far enough that no signal traveling at the speed of light could connect them. The spooky connection was real, and it could be produced and measured in the lab. Over the next decades, the distance over which entanglement could be demonstrated grew from a few meters to kilometers. In 2017, scientists in China used the Messias satellite to entangle photons and send them to ground stations more than 1,200 kilometers apart. The particles remained perfectly correlated, even when separated by the width of a country. Today, entanglement is not just a philosophical puzzle, it is a resource that can be engineered, distributed, and verified with precision. Quantum computers rely on this phenomenon to link qubits together, allowing information to be shared in ways that defy classical logic. The laboratory proof is clear. Entanglement exists, it can be controlled, and it forms the backbone of quantum technology. Quantum algorithms harness interference to find answers hidden in a sea of possibilities. In classical computing, searching an unsorted database of 1 billion items means checking, on average, 500 million entries before stumbling on the right one. Grover's algorithm rewrites this rule. By carefully tuning the interference between quantum states, it finds the marked entry in just over 31,000 steps, about 15,000 times faster than brute force. The mathematics behind this speedup is precise. The number of iterations required is approximately pi times the square root of n divided by 4. For a database of 1 billion, That means pi times 31,000 divided by 4, an operation count that would have seemed impossible before quantum mechanics. In 1994, Peter Shor showed that quantum computers could factor large numbers exponentially faster than any known classical method. Modern encryption relies on the fact that factoring a 617-digit number, RSA 2048, would take classical supercomputers longer than the age of the universe. Shor's algorithm, with the quantum Fourier transform at its core, slices through this barrier. The quantum Fourier transform, first formalized by Don Coppersmith in 1994, lets a quantum computer find the hidden periodicity in modular arithmetic. While a classical computer must check each possible divisor in sequence, a quantum computer explores all possibilities in parallel, then uses interference to amplify the correct period and suppress the rest. The result is striking. A problem that would require 300 trillion years classically could fall in hours on a sufficiently large, fault-tolerant quantum machine. Interference-driven algorithms do not stop at cryptography or search. Richard Feynman, in 1982, pointed out that simulating quantum systems on classical hardware quickly becomes impossible. Even a simple caffeine molecule, with its 158 electrons, demands tracking 2 raised to the 158th power, which is about 3.6 times 10 to the 47th quantum configurations. No classical computer, not even one built from all the atoms in the observable universe, could store that many numbers. Quantum computers, by contrast, naturally represent these vast spaces. Algorithms designed for quantum simulation use interference to zero in on the most relevant solutions, making it possible to model chemical reactions, materials, and biological processes with a precision that was once out of reach. The common thread in these breakthroughs is the mastery of quantum interference. By shaping the probability amplitudes of quantum states, quantum algorithms can make correct answers stand out while wrong paths fade away. This ability to amplify the right solution and cancel the rest is what gives quantum computing its edge. A new kind of speed rooted not in faster hardware, but in the strange, wave-like logic of the quantum world. Inside a quantum computer, the hardware reality is as extreme as the mathematics it supports. Superconducting qubits, the workhorses of today's most advanced machines, operate at temperatures near absolute zero, just 0.015 Kelvin colder than the vacuum of space. Achieving this requires a dilution refrigerator, a steel cylinder taller than a person, filled with nested chambers and cooled by a cascade of helium isotopes. At these temperatures, electrical resistance vanishes, allowing fragile quantum states to persist long enough for computation. Even so, coherence times for superconducting qubits are fleeting, typically between 100 and 500 microseconds before the environment scrambles the information. Trapped ion systems offer longer coherence, sometimes measured in seconds or even minutes, by suspending charged atoms in electromagnetic fields within ultra-high vacuum chambers. Other platforms, neutral atoms in optical tweezers, photons in waveguides, nitrogen vacancy centers in diamond, and topological qubits, each bring their own engineering trade-offs, balancing stability, speed, and scalability. The basic unit of quantum logic is the quantum gate. Unlike classical logic gates, which irreversibly process bits, quantum gates must be reversible, preserving information in line with the laws of quantum mechanics. They act as precise rotations of a qubit state on the Bloch sphere, a geometric representation introduced by Felix Bloch in 1946. The Hadamard gate, for example, transforms a definite state into a perfect superposition, while the CNOT gate links 2 qubits in entanglement. Pauli gates, X, Y, and Z, rotate qubits about different axes, forming the building blocks for more complex operations. Each gate operation must complete before decoherence sets in, demanding exquisite timing and control. The entire process unfolds in a race against the clock, as billions of dollars in engineering effort are devoted to keeping quantum information alive long enough to be useful. Quantum computers hold extraordinary potential, but their power is matched by their delicacy. Qubits, operating just above absolute zero, are vulnerable to even the faintest intrusion. A single stray photon, carrying 4 times 10 to the minus 21 joules at room temperature, can overwhelm a quantum processor, injecting far more energy than the system is built to withstand. Despite elaborate shielding, these disruptions are inevitable, turning fragile quantum states into noise in less than a millisecond. To counter this, researchers turned to error correction. Peter Shor's 1995 code encoded one logical qubit across 9 physical qubits, enabling detection and correction of errors without disturbing the quantum state. The surface code, introduced by Alexei Kitaev, pushes this further, spreading one logical qubit over roughly 1,000 physical qubits at current error rates. If the error rate per operation remains below 1%, the threshold, a quantum computer could, in theory, run indefinitely, correcting errors as they arise. Today's NIS-Q devices, built since 2018, offer 50 to 1,000 qubits with only partial error correction. Breaking RSA 2048 encryption is estimated to require about 20 million physical qubits, a milestone that may still be a decade or two away, yet quantum computers already serve practical roles. Variational quantum eigensolvers help model molecular structures, hinting at future breakthroughs in drug discovery. Since March 2017, IBM Quantum has provided free cloud access, allowing anyone with Python and Qiskit to experiment with real quantum circuits. Cryptography experts advise preparation, not panic. Qiskit contributors urge experimentation. Pharmaceutical researchers report faster simulations for active drug sites. The road to fault-tolerant quantum computing is long, but the chance to participate is here. Quantum computers are no longer locked in theory. They are running real code right now from anyone's browser. As industries race to secure data and accelerate discovery, the stakes rise. Quantum advantage could upend cybersecurity, medicine, and AI within years, not decades. The future is not just faster, it is stranger, and it has already begun. What would you do if you could harness the impossible? Share your thoughts below.